It's such a pleasure to talk about this topic. Forever chemicals is one of the hottest things that you will find in science right now. It's even gone into popular media. John Oliver had a scathing piece just a couple of weeks ago on his evening show about forever chemicals and how we got to this point. So in this talk, I'll give you sort of a background about what these chemicals are and why this is such a big deal and why this really changes the field of environmental engineering for the next 10, 20, 100, or 200 years. So first off, what are these forever chemicals? This forever chemical name has been around for a very long time. These chemicals were developed initially with the atomic bomb Manhattan Project in the 1940s, and very quickly thereafter, a number of companies, mainly DuPont and 3M, found multiple uses for these. These forever chemicals, the big term we'll use for them is PFAS. That stands for per and polyfluoroalkyl substances. And most of us don't have any chemistry background, or especially organic chemistry background, but I'm pointing to a few key little characteristics of these compounds. The first thing you'll see is there's a chain of atoms, these carbon atoms, that are completely fluorinated. This is extremely unusual. There are very few fluorinated compounds in nature, and those that do exist only have 1 or 2 fluorine atoms at most. But on these chemicals, the entire backbone is covered with fluorine atoms. It's completely anthropogenic, probably the most anthropogenic chemical we could probably think of. There's also usually some sort of N group, a functional N group. Here, this shows a sulfonyl N group. It's a sulfur oxide type of group, but there's all sorts of groups, and that changes the chemistry just a little bit. And there might be a spacer that also can influence chemical properties. But these things were such a major advancement chemically. It was widely celebrated in chemistry as a miracle sort of chemical with all these very unique properties in the environment. There is a bit of an alphabet soup when we get into these sorts of chemicals. So I won't try to make it too complicated for you, but PFAS, again, that's all of the chemicals, all right? That's the entire class. Any chemical that has some fluorine atoms attached to carbon and some sort of active group, we can call PFAS. It can be long, short, have all sorts of different properties. And from that, there's different ways we can categorize it. There are polymers of PFAS. PTFE is the most common. That's Teflon. I'll talk to you a little bit about Teflon. And then there's a lot of non-polymers. So these are individual compounds. And you can kind of break them out into various ways. But the two most major chemicals of those are PFOS and PFOA, which I'll also use. I won't use these other abbreviations on this page, but they're here in case you're reading into this literature and you see a lot more P something, something, something thrown around at you. Now, what are these unique properties? That perfluoroalkyl tail, those fluorine molecules, which is very unusual, right? That makes this chemical both hydrophobic and lipophobic. So it repels both water and fats and oil. That's extremely unusual. Most chemicals will either strongly prefer oils or water phases and then repel the other. But this repels both. That means it can be water resistant, it can be grease resistant, it can basically form a coating on just about anything, and both repel stains, oil, dirt, and water. That head group, though, is hydrophilic. Most often, it's not always, and that little group can attract water. That characteristic added to the other group does make these molecules able to be transferred decently easily in a lot of water and air systems. It doesn't really like to be in the water systems individually, but it can form these little micelles and these other sorts of structures where it will be relatively stable in the water system, stable enough to move a long distance downstream and spread globally. And we do find these chemicals spread globally. Now, fluorine is one of the most electronegative element on the periodic table. So All chemistry is made up of all of these different kinds of elements. And fluorine is the most electronegative, meaning it really, really loves to hold on to its electrons really tightly, real tight. So when fluorine is bound to something like carbon, which is in everyday substances, most of our dry weight is going to be in carbon, that fluorine will still hold a very strong amount of the electrons. And then the carbon gets kind of robbed from that. So that induces this sort of dynamic where you have a negative charge around the fluorine and a partial positive charge around the carbon atom. And that really helps give it this strength. The strength of that bond is one of the strongest bonds in nature. It's sometimes called the strongest bond in organic chemistry because it's the strongest carbon something single bond that exists. A lot of the strongest bonds in nature, like nitrogen-nitrogen, which forms a lot of our atmosphere, is no more than double this amount. Now this is about 4 times the amount of energy associated with this bond, and it's normally associated with a lot of carbon atoms, like carbon-hydrogen bonds, etc. So it's a very, very tight bond, and that's because that fluorine's really holding on to those electrons tight, and it does not want to let that go. The other problem, or miracle of these chemicals, is that fluorine molecule, those fluorines really kind of shield that entire carbon backbone from being able to get attacked by anything. So most enzymes and things that will break down a chemical, you have to get at that carbon atom. But these fluorines really provide this protective shield around that carbon atom, which makes it extremely difficult to degrade. So it's very hard for enzymes and other things to really get at this structure to break it apart. So they're called forever chemicals because they really don't degrade. They repel fats and oils, so there is a huge amount of industry that can benefit from this and personal uses that can benefit from this, right? Repels water, and it really doesn't burn. So it's something that can be used in a lot of cases where you need fire resistance. Now, won't degrade, I always think, exclamation mark, as an environmental engineer that studies the degradation of a lot of compounds. We typically want things to degrade at some point, right? Otherwise, where does it go and why we'll never get rid of it? And won't degrade was really in the 1940s, 50s, 60s, etc., was seen as this very unique, useful characteristic. You don't have to worry about its shelf life. You don't have to worry about its degrading on you. You don't have to worry about its burning if you use it. And in celebration of these sorts of things, firefighters would hose children down with these compounds because it's slippery and fun to play with and such a miracle chemical, right? So this is a real newspaper clipping where the Rotary Club in Pennsylvania was at an Easter Seals camp and letting the kids play in this firefighting foam made of these PFAS chemicals. This is now one of the big sites that is contaminated with these chemicals, and there's a lot of problems associated with that now. So what are all these uses? One of the main uses, of course, has been Teflon. Teflon is made from this chemical PFOA, perfluorooctanoic acid. All right, so PFOA is one of 2 very specific types of PFASs that I will talk a bit about here and there. PFOA, this was one of the original compounds, or the original real compound, that really kick-started organofluorine chemistry in the Manhattan Project. And DuPont immediately saw the potential in this sort of chemical to make these polymers like Teflon. And Teflon polymer is one of the most widely and successfully marketed things that have come about in commercial goods. Nowadays, DuPont has shifted this off into another spin-off company called Chemours, which is probably to shield some liabilities and problems associated with making these chemicals. Chemours has quite a flashy website, still talking about all the great uses of Teflon. Nowadays they make Teflon with Gen X, which is a compound that has replaced PFOA because PFOA got so much attention in the last 15 years for toxicity effects. Unfortunately, Gen X also looks to be just as toxic and maybe even more problematic in terms of movement in the environment because it's a shorter chain of that carbon fluorine system, meaning it can transport farther distances in waterways. But Teflon, you will recognize it all over your house. It's all over my house. It's all over my lab. You'll find it in baking sheets, nonstick cookware. They put it into paint. They put it into water repellent outerwear. They'll put it in glasses so that you can see clear through your eyeglasses. They use it in fishing line because that oil and water repellent properties will prevent fishing line from tangling up. They can use it for umbrellas. Most of these pictures came from Chemere's website. This is part of their marketing. You'll find it in tape. You'll find it in appliances you use, solar panels. You can floss with Teflon. You can bake chicken on it. You can use it for seals. You make cheese out of it. All these cheese molds. I actually have 2 cheese mold pictures on there. You can see how much I like cheese. But cheese molds have Teflon because it's non-stick. Your cheese won't stick to the little mold you have, meaning you can pull it off quite easily, saving you, a little bit of minor headaches washing dishes. They will coat tools with it. They will coat door handles with it. It's been used in all sorts of grease particles for bicycles, to coat irons. If you Google on Amazon, or Amazon search, I should say, Teflon, there are over 8,000 results of items marketed as having Teflon on them because of this, oil-resistant, water-resistant property. Lots of uses of Teflon. And Teflon is a polymer, which does give it a little bit less concern from a public health standpoint. Once you have a polymer, meaning the large string of a compound, that's harder to really get into your cells to cause much toxicity. So when it comes to a lot of Teflon goods, the concern is with chemicals that might be released from the Teflon. It's from, from a pan. If it gets heavily scraped or something, you're going to release some of the chemical. Or if it overheats, you might release some of the chemical. But if the polymer just sits there, it's not going to be the biggest risk to most people's health. Because it is in this polymer form. So it has to break down a little bit, which is something that concerns people still. And people have been switching to things like ceramic cookware. Now, another major compound is PFOS. So we just talked about PFOA, used to make Teflon. PFOA is used in lots of other uses as the individual compound. In PFOS, this is perfluorooctane sulfonic acid, is what the 3M company really focused on from the 1960s till 2002. PFOS has very similar chemical properties. 3M put it sit in Scotchgard. Recently, Scotchgard no longer has PFOS. I'm not sure what they have replaced it with. They won't really give away their trade secrets so easily. But Scotchgard and a lot of 3M products, you will not find PFOS used anymore. 3M has stopped making PFOS in 2002 and phased it out of their products. But they used to put it on almost all their products, like even sticky notes, Sharpie markers, because it provided a nice oil-resistant, water-resistant surface. PFOS has been used very heavily, though, in firefighting foams, which is one of the pictures shown here. You see someone putting out a fire with a firefighting foam. It's very effective with firefighting foam. Usually it's mixed with PFOA or Gen X in some of these uses. It's also used in the oil field. I have some studies with what's used in like hydraulic fracturing fluids, and every once in a while, PFOS will be used to help kind of keep things lubricated and moving along when you're drilling for oil. A lot of PFAS, so talking now more about the broad chemical, is really in food packaging. When it comes to consumer use, there has been, a lot of concern about a lot of these chemicals. I mean, it was even put into like things like eye makeup and things that you might shampoo yourself or put on your skin, like some suntan lotions and stuff. Right now, the biggest concern from a consumer standpoint is with food packaging, because it's still very heavily used in food packaging, and it's very hard to know if anything has PFAS in food packaging. It's not going to be labeled with PFAS, it's not going to be marketed with PFAS, but a lot of food packaging will have PFAS in there. Now, popcorn is one of the major routes of exposure that we are quite sure of. Popcorn bags, the microwavable popcorn bags, have a lot of PFAS, and you're going to heat that up to very high temperature when you pop popcorn, and so there's recommendations to let that kind of air out of the chemical after you pop your popcorn, if you still love your microwavable popcorn after this lecture. Big Whopper, wrappers. And the thing about this is that, even like the health foods sort of aisle is going to have PFAS. Studies have looked and found that, it doesn't matter if a product's marketed as natural or organic. There's just as likely of a chance that there's PFAS found in that packaging. And a lot of these are sourced from global supply chains where we may not always be sure the entire history of that product and who's touched it and has made it nonstick. But all these nonstick surfaces. And food packaging is one of the things that has been correlated with how much people have in their bloodstream. So 99% of Americans have some sort of has PFAS in our blood. I can guarantee you I have PFAS in my blood, and you probably do too, to some level. And one of the things that has been correlated with the amount of PFAS in blood in the US is really how much someone eats out versus cooks at home. And people who eat out more tend to have a higher level of PFAS in their blood serum. And a lot of the concern about PFAS is contaminated water, which I'll talk more about in a bit. So what are these health concerns? A lot of these health concerns were first alerted in 1960s and 70s. And like a lot of things were hushed down and not discussed and kind of was always at the back burner of things. In the last 10 to 15 years, the health concerns of these compounds have been looked at with increasing frequency and increasing scrutiny. And it has been well linked in both studies of animals as well as in certain cases of human exposure, such as people who have lived at these sites that are well contaminated with PFAS, or people who've worked in the industry and were breathing in and touching PFAS every day. In those kinds of cases, you can do a statistical correlation to determine health effects from chemical exposure. In the general population, it's very hard to do that because of all the environmental factors we're associated with. But thus far, it has been pretty well linked, either with animal or human data, to kidney and testicular cancer. Liver and the kidneys seem to bear heavy brunt of the chemical in our body when we try to deal with it. It has been linked to thyroid disease, decreased fertility, hormone disruption, liver damage, decreased antibody response to vaccines, which is something we kind of care about the last couple of years. We want our vaccines to work. Lower birth rates, higher chances of asthma, increased cholesterol, pregnancy-induced hypertension and preeclampsia, cardiovascular disease, and so there's a lot of attacks in our system, and a lot of that is because those PFAS compounds look a lot like our membranes, our cellular membranes that kind of protect our cells and regulate the transfer of chemicals in and out of it. So these PFAS compounds do have a tendency to kind of sneak into our membranes and cause toxicity effect. I'm not a toxicologist, so I can't really speak too heavily about the toxicology of these things, but it is now well known and out there. Now, as I said, 99% of the US, and you'll see other people say 95%, 96%, depends on what study they said. That 1 to 5% of people who had no detectable PFAS, I would probably guess that's probably a false negative, right? Because PFAS spread is worldwide. It is found in blood throughout the world. It is found in blood in places fairly far away from heavy consumer uses of PFAS products because it does transfer through the air and through the water fairly readily for a chemical. PFAS does bioaccumulate, so it will tend to accumulate in our bodies. And the best estimate is that most of these chemicals take about 5 to 8.5 years to have themselves in our body. So if I was not exposed to any PFAS today, it would take 5 to 8.5 years before my PFAS concentrations were in half. It would take another 5 to 8.5 years before it was halved again. So we're all going to die with some of this in our body. It will be in our caskets with us, which is pretty dark because none of us signed up for it. So what is the current status of these sorts of chemicals? Now, PFOS and PFOA, these two specific chemicals I have mentioned, they have been slowly phased out nationwide, but they're still produced in many parts of the world. China, for example, still produces these chemicals. We sometimes call these long-chain PFAS compounds or C8 PFAS compounds to refer to the number of carbons in that chain that is fluorinated. But since a lot of the early studies or earlier studies found the toxicity with these compounds, they were very quickly seen as liabilities and problems. And 3M, for example, stopped making PFOS in 2002. And they have hired a lot of environmental engineers. A lot of the colleagues I went to graduate school with at the University of Minnesota got hired by 3M to really try to tackle the PFOS liability that they have to deal with. Shorter chain PFAS compounds have replaced a lot of the PFOA. GenX is one of these compounds that's used to make Teflon nowadays. It's a shorter chain, which the thinking about making that carbon fluorine sort of tail shorter was that it would bioaccumulate a little less. And it does bioaccumulate a little less. The problem is that it is more mobile in the water and has, it seems thus far, just as much toxicity as the PFAS and PFOA compounds it's replacing. And I don't know why they called it Gen X. Gen X is the generation that everyone forgets about nowadays, right? And then they named the chemical after that or something. I'm not sure how they come up with it. Firefighting foams. Firefighting foams is one of the major sources of contamination in groundwater. Firefighting foams used by the military and commercial airports, you will see here in a bit, is the source of most of the point source contamination that we have like here in Oklahoma. Firefighting foams did shift to shorter chain fluorocarbons, which were supposed to be a little better. And the Department of Defense has spent a lot of research and money to try to develop better fluorine-free foams. All right, so they've had fluorine-free foams since about 1985, but a lot of them are not as effective with high temperature fires that are going to be associated with aircraft crashes or boats on fire, like naval ships on fire and stuff. So they still are trying to find the right types of fluorine-free foams that can perform as well as the PFAS foams that they have relied on. So they've had large stockpiles. From what I can tell from their communications they put out, a lot of those stockpiles have been sourced and have been somehow eliminated, or at least is being reduced. And there is current advisement out there on military bases to only use any stockpile of a PFAS foam as a sort of last resort. Like, don't use it, don't train with it unless it's the only thing available. PFOS, that chemical, has been banned in Europe since about 2009, but again, these things being involved in global supply chains doesn't mean that a ban is 100% effective. Long-chain PFAS is still permitted for use in metal plating, semiconductors, photography applications, hydraulic fluids, and aircraft. So we still use some of the even traditional compounds because they can still be imported and used, and they are permitted in a couple of these cases here. And we're going to have direct and indirect exposures to these chemicals well into the future because there are thousands of tons of these things produced and have been released out there. And there's going to be continuous releases out there even after a ban because of just how widespread these things are. I mean, it's been used in practically everything, right? So the problem that is really developing is that every time a PFAS chemical is targeted, more PFAS compounds are made and developed and then used without proper testing and consideration. All right, now one of the big announcements from the EPA was yesterday. In February 2021, this was just last February, the EPA did announce that they were going to start moving towards implementing national priority drinking water standards for PFOA and PFAS. Now, drinking water standards is one of the major regulatory tools that the EPA has at preventing us from drinking toxic chemicals. There are over 100 chemicals that have these regulations on them, and every water treatment plant that basically serves the public has to test for these chemicals on a regular basis, report what the concentrations of the chemicals are, if there are any problems or any chemicals that are in exceedance of that, there has to be a notice provided to the public. You have to have action to clean it up. So putting these PFOA and PFOS compounds on there is a big step. There have been calls to do this since early 2000s. Yesterday, they announced a strategic roadmap. So they put out this nice flyer. I think it's about a 10-page document. It's not super long. The link to the document is here, and then the EPA's general PFAS link is also provided here, where you can see more about the EPA's communications about what their plans are. So the roadmap, to summarize it, I didn't read the entire thing, but because it just came out yesterday, but I did glance over it and try to see what the key points were. PFOA and PFOS, these two compounds, the one produced by DuPont for the longest of times to make Teflon out of, and then PFOS, which 3M made for the longest time for firefighting foams, they're going to try to have the maximum contaminant level, this regulation for drinking water standards, by the fall of 2023. So it's still a couple of years away. They have to determine what is the level of compound that they will accept. And that should be based on the level of chemical that is safe. That is not a trivial thing to determine. With that regulation, there has to be increased testing, standardized testing, and monitoring of PFAS in waters and fish. So they have plans on how to increase testing and standardize it. They plan to test every public water system between 2023 and 2025. That is needed to do a drinking water regulation. You have to test for these chemicals, not just once, but over a regular basis to prove to the public that you're not in violation of the Safe Drinking Water Act. Now, this is a big step. A lot of water systems are not tested for PFAS. It is not a cheap method. It is not an easy method. And only in states that have had special action to basically monitor these chemicals, only in those states have a significant number of drinking water treatment, tap water has actually been tested. Oklahoma is not one of those states. They plan to publish final toxicity assessments on some of these new chemicals like Gen X and at least issue health advisories. A health advisory is not binding, but it's generally the EPA communicating what level they think is safe. Right now for PFOA and PFOS, they have a health advisory for drinking water of 70 parts per trillion, which most people think is way too high. From people I talk to, anyways, the industry thinks that is fine. So the things that have to occur is that PFAS discharges into waterways, of course, have to be restricted. There are still cases in the US where PFAS is being discharged into public waterways, and that will have to get stopped and restricted in order to have compliance with these sort of rules. And a really big step that I'm not sure too many people have paid attention to yet is that PFOA and PFAS will be a CERCLA hazardous substance. CERCLA is most often people know that as the Superfund Act. This was an act in 1980 that really kind of identified contaminated sites and either force the responsible companies to clean them up or use a tax-based source of revenue to pay for the cleanup costs of sites they couldn't get someone that had money and that is responsible to pay for it. So designating PFOA and PFAS as a circular hazardous substance is a really big deal because that means that sites that are heavily contaminated might have to get cleaned up. The companies responsible for the dumping will have to pay for it if they are still financially solvent, and otherwise chemical industry taxes might have to prioritize which ones can be cleaned up for the biggest effect, and then over 100 or so years it will be a major source of jobs for environmental engineers, it looks like. All right, risk assessment also needs to be done for PFOA and PFAS. And one of the things they said about risk assessment is they want to do it in biosolids. Biosolids are a product of wastewater treatment. So when we flush our toilets and everything goes down the sink, it all goes to the wastewater treatment plant. And from that you get decently clean water. Usually the water that leaves that plant is way cleaner than the creek that gets it. So rivers basically get a little bit cleaner when wastewater that's been treated gets discharged into it. But there's also going to be biosolids, and that's mostly the microbes and things that have degraded all of the organics and fats and things that are in the sewers. So the thing about biosolids is it also becomes a very attractive sort of dumping ground for chemicals in the wastewater treatment process, because any chemical that prefers to be on the solid versus the water will accumulate on that biosolid. So like microplastics, also a big deal, something you might hear a lot about. Microplastics mostly accumulate on the biosolids. Most chemicals will accumulate on those biosolids. And so that becomes this unique sort of source of contaminant concentration that otherwise doesn't occur in nature. And the thing about biosolids too is that a lot of that gets applied onto lands where it then can enter food webs. Some biosolids are placed directly into agricultural fields where that provides nutrients for crops. And if that biosolids has PFAS, we might want to know because then we're loading up our potatoes and corn and things with PFAS, which we may not want to eat. All right. Now, back to the current advisory limits. So a number of states have put out advisory limits. Again, these are typically not going to be enforceable, but they're typically like levels the state wants to determine, basically like how many tap water systems, drinking water systems have contaminant levels above a certain amount, right? And you'll see over time, this shows years 2002 to 2018, that a number of different guideline levels have been established. I don't know what West Virginia was doing in 2002, but they had a guideline of 100,000 nanograms per liter or parts per trillion. Most people say more than 1 part per trillion is probably hazardous to your health. New Jersey has the lowest current advisory limit out there. And the most up-to-date website is actually linked here on the bottom. It's an environmental Wikipedia sort of website on perfluoro and polyfluoroalkyl substances that a couple of environmental engineers at other universities keep up to date. And currently there are 9 states. You can't see what they are here, but basically it's New Jersey, Michigan, North Carolina, and Texas even, Illinois. These 9 states have some sort of advisory limit. Oklahoma is not one of them. And sometimes it's in water and groundwater and or soil, or just on one of those media. The EPA's health advisory limit is set at 70 nanograms per liter in drinking water, which is a level that the industry kind of puts out there as what they think should be any sort of contaminant level. Again, that's 70 times higher than the 1 part per trillion that most World Health Organizations put out there as a target. In this slide, I'm basically just showing that each of these states, they use different sorts of toxicology data to kind of set up their different advisory limits, because The way that these things usually work is that, we all want zero contamination. We want perfectly clean air and water, but that's not practical, and it's not measurable. You can't measure zero. So you put some number based on toxicology data and exposure amount. So there's a calculation that goes into this, like how much water do you drink, times the concentration of the chemical in the water, how much is that going to accumulate in your body, and then is that enough to cause a health effect? And so they're using different health effects. Some of these are using the data based on lactating women. Some are using adult sort of liver toxicity sort of information from various studies. And that's why you have all these different numbers. And the EPA has to sort out what of these toxicology studies should set our limit, and then what kind of safety factor, if any, should be put on top of that. All right, now in the current legislation in the US Congress, there are 44 bills this year that have at least mentioned PFAS. These bills range very widely. Some of them are very focused on PFAS contamination problems. Some of them are focused on things such as, funds to help firefighters that have been exposed to high amounts of these compounds. Sometimes PFAS gets written into a small section of a much larger bill. So this 44 is all-encompassing of every mention, or every bill that at least mentions it somewhere in the legislation. These bills are mostly just sitting there still. In Oklahoma, I found a single bill that mentions PFAS on the last legislation session. I looked at about 6 different websites and source search functions, and only this one ever came up. And it was looking at basically establishing some liability for PFAS waste generation and responsibility. It did pass the Committee on Energy in the Senate, and then it basically just died because nobody else picked it up, and it didn't get heard by the full Senate. So at least the legislatures talked about this once in the last year. All right, now moving on to contamination. So what is the current state of affairs on contamination? It's a very difficult sort of issue because it's hard to even know exactly how much of these chemicals were produced. It's produced globally. There's thousands of actual chemicals that have been produced, and there's tons of ways these have moved through the environment. They can move through the air. Since this does not burn until you're at least 1,000 degrees Celsius, in sort of like municipal incinerators, if they're not hot enough, this PFAS doesn't get destroyed. It just gets released into the air where it transfers. Also, in certain kinds of industrial processes, you have air releases of PFAS. You have PFAS contamination in soil. You have it in the groundwater. Every time there was a firefighting training exercise or a real fire using these firefighting foams with PFAS in it, that's a source of contamination that is still going to be there today. Landfills will also have leachate. So that is the liquid that basically seeps out of a landfill. We've identified fairly high concentrations of PFAS and landfill leachate, and finding ways to kind of absorb that and put it back into the landfill or do something with it, maybe destroy it, has been a priority. So I will only barely really touch on the contamination problem. I will first off just point to a recent study that I saw come out this year by Jarvis et al. This was just a very nice study looking at surface water and the chemical PFOS. So this is 3M's old chemical. They looked at the Great Lakes region and a number of states, took a number of samples from each state, measured the amounts of PFOS in there, just this one type of PFAS compound, and published some data. And if we think about that 1 part per trillion level, that's right here. That's 1 part per trillion. This is 1 part per trillion. You see that the Great Lakes, with the exception of Lake Superior and maybe a few parts of Lake Huron, have more than 1 part per trillion in the lake. All right, so it's already in the lake. When it comes to surface water, There were ranges between very low levels, 0.01 part per trillion, that's probably not a concern, but up to 100,000 parts per trillion in some cases. Some of the highest samples, one here is Alabama. This is because Alabama was one of the major producers of PFOA in the US for a lot of years, and there is a lot of contamination from that production site. Florida, North Carolina are also major areas where this chemical has been produced and used very heavily in industry. Minnesota, of course, because of 3M, based up there in St. Paul, or very close to St. Paul, Minnesota. There are a number of waterways, especially just south and east of the Twin Cities, that have high levels of PFOS contamination. So a lot of the places that are really high are not surprising, but what is somewhat surprising is even far downstream locations can still have fairly high amounts of PFOS that has traveled there or has come from unidentified sources. So without testing, we don't really know for sure where it is, even in surface water. Now back to this map. This map is from the Environmental Working Group, EWG.org. The Environmental Working Group is a nonprofit that has been around for quite a while. They have focused very heavily on documenting the science of PFAS contamination in the US with a special attention to drinking water concerns. And they have a map that they do their very best to keep up to date. The current version has been updated as of October 4th, 2021. And it's a compilation of various data sources for PFAS contamination in drinking water supplies. You will see here that there is not a lot of data in a lot of states. Places like New Jersey, North Carolina, Alabama, Michigan, in Colorado's, their efforts are a bit more recent, but very heavy and widespread. Because these states have these health advisory limits and have invested locally into testing for PFAS contamination, they have tested many, many more public water utilities and groundwater sites than places like Oklahoma. The data we have for Oklahoma only really comes from two sources. One is the military, and one is from a very cursory overlook of PFAS contamination done in about 2014. So where in Oklahoma are these sites? We might as well point them out since we're talking about them here. One of the heaviest contaminated sites is in Enid. This is Vance Air Force Base. They are heavily contaminated with firefighting foam, as are just about any military base in Oklahoma. Their parts per trillion are 71,000, 18,000, 12,000. So if one is kind of the health limit, we are 71,000 times too heavy in this groundwater, meaning that it's effectively not going to be able to get used for drinking water anytime ever, probably. When it comes to places, this is Altus Air Force Base. That has hundreds of thousands of parts per trillion of different kinds of PFAS. In Oklahoma City, Tinker Air Force Base. Tinker Air Force Base, being such a large Air Force base, has a number of contaminants in their groundwater. So this is just basically one more thing that has contaminated the groundwater there. Again, from firefighting foams. And the firefighting training facility in Midwest City just near there, also, of course, contaminated with firefighting foams as expected. The Midwest City Readiness Center is what it's called. The Oklahoma City Airport, also contaminated with firefighting foam. This is in the tens of thousands of parts per trillion. And in Tulsa, the Tulsa Airport, International Airport, has thousands to tens of thousands of parts per trillion of PFAS and PFOS. And the Air Force plant, I think it's plant number 2 or 3, I can't read so well, but right there by the airport, also tens of thousands. Camp Gruber down there by, what is that, Greenleaf State Park, I believe. Very nice little state park. Camp Gruber is kind of behind that. They have a little bit of PFAS. These levels are fairly low. This is about 1 part per trillion. Now, when it comes to drinking water, the only real case of drinking water is in Bethany. There's another dot on this map for drinking water, but I think it's a mislabel. It actually refers to a place in an entirely different state. So Bethany, Oklahoma, they were alerted to their problem in about 2014. It stems from a couple of companies located at Wiley Post Airport. So Gulfstream and Rockwell International. Lawsuits were filed. I'm not sure the status of those lawsuits. I couldn't find a news release any earlier or any more recent than 2019 on this. But Gulfstream and Rockwell are believed to be the causes. They have blamed Bethany's sewer systems as the cause, which is a little bit hard for me to imagine as an environmental engineer how that could actually happen. But because of this contamination, they have had to turn off 2 of their groundwater wells that they source for drinking water, and they've spent millions of dollars now testing their other wells to make sure that the contaminant isn't there yet. So right now their drinking water is safe. They do test it regularly for things like PFAS and PFOA, but there's also a lot of other contaminants from this airport that they've had to monitor over the years. But they have had to do a lot, and these 2 companies have helped in some ways at trying to limit the spread of this contaminant plume in the groundwater from reaching those other wells that they are using for their source water. Now, in Oklahoma, we don't know a whole lot about our drinking water sources. On one hand, we don't have a high amount of industry believed to have used heavy amounts of PFAS and PFOA. On the other hand, we have these military bases, firefighting training facilities, and so we have our known point sources. How far have these point sources spread is still left to be unseen. So I was recently, a couple of years ago, awarded a Fellows Faculty Research Award to basically at least start setting up the equipment in my lab to start studying these compounds. This work is still underway. This is what an instrument looks like that can monitor these compounds. It's a very sort of expensive types of instrument and expensive type of process because all the reasons that make this chemical so stable also make it hard to detect analytically. So this machine can do so, and we are this close to finalizing our methods. Once finalized, I do hope to collect about 80 water sources in Oklahoma myself and see what kind of levels of PFAS I can find. I'm especially interested in finding anyone that has groundwater wells, private groundwater wells, anywhere near these sorts of known contaminant sources, just so we may have some idea if this has spread that far beyond the base. I'm sure the military is also monitoring these things, but they don't always release this data up to date if they don't have to. So what do we expect to find? Really, most places probably will have somewhere between 1 and 15 parts per trillion of PFAS as background. And this basically is what New Jersey has found. They have found a number of hot spots, especially cities that use rivers with a lot of industrial uses, where levels are much higher, such as Camden, New Jersey. But most of these municipalities have levels somewhere between 1 and 14. That might be acceptable underneath whatever new regulations come up. It may not be acceptable. So the more we know, the better, especially if you want to be ahead of the game here. And then beyond just drinking water sources, there's still a lot to find out about all the different ways in which this contaminant might get to us. We know it's in landfill leachate, but how many landfills are leaking that we don't know have this? What is this real level in biosolids? There's a lot that we don't know about biosolids and how that might transfer onto crops. And so I've been trying to look for some research funding to continue this work forward. Now, when it comes to treatment, remember, it doesn't degrade and it doesn't burn, or at least it doesn't burn unless you're about 1,000 degrees Celsius or 1650 degree Fahrenheit. That's hotter than a pizza oven, hotter than the ignition of coal. And again, if you don't get it hot enough to destroy the compound, you end up just releasing it into the atmosphere, which is not what you want to do. So to incinerate this is possible, but it takes care and it takes expertise to do so correctly, so you just don't mobilize it. In drinking water, there's a number of technologies that can be used and are used. One of them is activated carbon. These sorts of systems can also reduce taste and odor problems. They can reduce pesticides and personal care products, sort of chemicals, estrogenic chemicals and things that might be in the water. So there are other reasons to use activated carbon. It is not very widely used because it's somewhat expensive. It costs about $1 per 1,000 gallons. That would raise your water bill something like 15% from where it is currently, just to have an activated carbon system in there. So there's a cost associated with it, but there is a technology. Activated carbon does perform pretty well with the long-chain PFAS compounds, as long as the pH isn't too high or there's too many salts, because that can interfere with absorption. You just need enough units that you have enough contact and area and time, and then you have to dispose of it. A lot of the headaches about activated carbon is just the trucking of this material, disposal of the material, and handling of the material, and the cost, of course. And there's a number of activated carbon chemicals that are specifically designed and tested for PFAS removal, such as this one from General Carbon. Ion exchange resins are also something that people use. These are beads and polymers that can bind up PFAS. So it's like activated carbon, where the PFAS will stick to this. It's a little bit more engineered. Activated carbon is basically like coal that's been steam treated to basically become absorbed. Ion exchange resins are like engineered materials with specific surface properties to get that binding that you need. This at least can do short chain PFASs that don't bind very well to activated carbon. The problems here that water has to be clean. Any sorts of oils or grease or other contaminants in the water can interfere with this. But if it's tacked onto the end of a water treatment process, it can remove PFAS. Again, it's going to be expensive, just as or a little bit more expensive than activated carbon even. And there's a number of commercial companies that have developed, marketed, and any municipality can go ahead and set this up. You know, it's all, technology's all there and understood. High pressure membranes, nanofiltration and reverse osmosis also work really well at PFAS. The biggest headache with this, so in the resins and the activated carbon, like you can burn that, you can maybe landfill it carefully because it's a solid that you can collect and then dispose of. With high pressure membranes, you have a liquid side stream that's basically the concentrated pollutant. And being a liquid is a little bit harder to deal with as a hazardous sort of waste. So it works well, but there's a high energy cost, and what's left over that has the PFAS in it is going to be a little bit harder to deal with. Membrane systems are being installed in a lot of water treatment systems for other reasons. Usually it's not nanofiltration or RO. Usually it's a little bit of a bigger membrane source, but it can block bacteria and viruses and treat that out of the water very effectively. There's also advanced oxidation options. These options are very kind of cool. I really like them. I'm not an expert in advanced oxidation. I know people here at OSU who are. But you can, focus a lot of electrons and energy onto the chemical and actually destroy that fluorine off of it. Battelle is a very large environmental services company, and they have a marketed product for PFAS destruction where you can, you really kill the chemical and not just move it. And won't degrade is still a little bit of a question mark. My background with research is very focused on bioremediation, especially of chlorinated compounds, which are like fluorinated compounds, but the chlorine atom can come off of carbon through a number of microbial processes. It took a couple of decades to figure out, but it will microbially degrade under the right sorts of cases. And there's still a lot of hope that we can find a way to use microbes to degrade PFAS. The benefit of microbes degrading PFAS is then there's hope of actually destroying the compound in all of these groundwater sources, all right, where it's very hard to remediate, especially as things get dilute without some sort of microbial action. One of the seminal papers on this has come out just a couple of years ago of this. It's called an acidobacterium. Basically, this microbe does something rather ordinary. It can eat either ammonium or hydrogen, and then it basically will breathe or shuttle its electrons onto iron. And irons are in groundwater everywhere. So this has sort of some capabilities that could be used perhaps to degrade PFAS. It can actually separate the fluorine off of the carbon, which, I was saying very early in this talk, very difficult to do, practically thought impossible, but this microbe has a way to do it. And they have the evidence showing free fluoride release coming off of these molecules as it's degraded. It's not an energetic process to remove the fluorine, so the use of this would still have to be very heavily engineered and still somewhat expensive. But if there's one microbe out there that can do it, maybe there's more. All right, now the other headache is co-contamination. Most of these compounds, these PFAS compounds, are contaminating sites that have had other contaminants, such as trichloroethene, dichloromethanes, and things. And so the problem with PFAS is that it basically is toxic to microbes, and it shuts down microbial processes. So not only is PFAS hard to degrade, it makes bioremediation of other contaminants even more hard than it used to be. So what's the bottom line? The most up-to-date number is that probably 200 million Americans are drinking water with more than 1 part per trillion. Well, if you switch to bottled water, there's no guarantee it's any better. In fact, it could be much worse depending on where that bottled water came from. There's probably 18 to 80 million that have more than 10 parts per trillion. There's a lot of big gaps in that data, so there's still a lot of research that people like me need to do to really kind of understand where these exposures are coming from, how much are we drinking, especially when it comes to locality, and so that we can focus really these efforts where we kind of get the most effect for public health. Regulations are in the works to set maximum contaminant levels for PFOA and PFOS, but there are hundreds, thousands of PFAS compounds. So when that EPA regulation came out, many people applauded it. It's good to have action. A lot of people have been calling for action for 20 years, but it only addresses 2 compounds specifically when we know that there's going to be perhaps hundreds of compounds with the same toxicity, very high levels of concentrations in certain cases. We might as well tackle those things at the same time versus waiting until everything else is done. So this is going to dominate environmental engineering for the next decades. It's hard for us to ignore. We're going to have to measure it, monitor it, treat it. We might have to pay more for our water to save. The benefit of using activated carbon, though, is the water will taste better if we do spend that 15% extra. So it's not all bad. Where the regulation is set in the next 3 years or 2 years is going to matter a lot. If it's at 70 parts per trillion, there may not be a whole lot of action that's required of anyone. This is a sampling that was done by the Environmental Working Group. It includes a tap water sample from Tulsa, Oklahoma. They measured something like 3 to 4 parts per trillion, which is not real high, a little bit higher than we probably would want it to be. But if the EPA sets a limit at 70 part per trillion, which is what the industry is proposing and wants, only a few municipalities may actually have to have action with drinking water treatment. If it's 1 part per trillion, just about every municipality will have to have action with regards to treatment. It might be somewhere in between. Hopefully it's based on science and toxicity data and not what the industry wants for the health and benefit of all of us. So the other question is, how much will the public accept? If the public knows about these risks and the toxicity and the EPA sets a regulation a little bit higher, will the public accept that, or will there be communities that still rally for bond packages to insert better quality drinking water? I am not so sure what this future looks like, but we're all going to live it. So that's the last slide. I thank you for watching me talk up here, and I have time for a couple of questions.
Okay, so far we don't have any questions that have come in for the chat, but I just want to thank you so much for for taking the time to talk to us about this really important topic.
Thank you.
Indeed,
And it looks like I went a little bit over on time. I can get a little chatty sometimes. So thanks for bearing with me. But if anyone has any questions, this is my email address. And again, if someone has a private well water that they want tested with my round of samples, feel free to drop me an email. It might be possible that I can take a visit, take some water, and include that in my sampling. It will be easy for me to get tap water samples from municipalities, but private well water is a little bit harder for a researcher to locate people who are willing to participate in such a study. So I'm very open to any invitations for that.